All right, welcome everybody. Today we're going to talk about Calc Lesson number 7, and this is section 1.5, which is all about infinite limits. This is the final section in chapter 1 before we have our chapter 1 test. So functions that increase or decrease without bound are said to either approach positive infinity or negative infinity. These are called infinite limits. Before we actually get into the mechanics of it, I just want to make sure that you can actually think about what it would mean to be approaching infinity or what it would mean to be approaching negative infinity. Before we do that, let's consider the following. If I was to tell you to divide 1 by a positive big number, and it doesn't have to be 1, it could be 10 or 100. The idea is the same. But let's say you were dividing 1 by a positive big number. So let's say you were dividing 1 by a million. If you were dividing 1 by a positive million, you would get a very, very, very small number, and it would be a positive small number. So if you divide 1 by a positive big number, you get a positive small number. And as this number gets bigger and bigger and bigger, this answer gets smaller and smaller and smaller. And as far as we're concerned, it's basically 0. What if you were to divide 1 by a negative big number? So let's say you were to divide 1 by negative a million, you would get a negative small number. And again, what if the number in the denominator is getting bigger and bigger and bigger? Well, then your answer is getting smaller and smaller and smaller. And as you get smaller and smaller and smaller, you're essentially reaching 0. So if you understand why 1 divided by a big number is essentially 0, I would hope that you could understand why the opposite would be true. So let's say that you were dividing 1 by a positive small number. If you divide 1 by a positive small number, you're going to get a positive big number. And as this number gets smaller and smaller and smaller, this number gets bigger and bigger and bigger. The biggest positive number that exists is essentially positive infinity. What if you were to divide 1 by a negative small number? You would get a negative big number. As this number gets smaller and smaller and smaller, the answer gets bigger and bigger and bigger. What is the biggest negative number? Well, that's essentially negative infinity. So I kind of just want to set the scene, kind of have your brain thinking about what it would actually mean to have an answer that either goes to 0 or that keeps getting bigger and bigger in the positive direction to infinity, or that keeps getting smaller and smaller to the negative direction of infinity. So just to kind of set the scene here. Infinite limits are very easy to find from graphs. Now, you have a lot of resources at your disposal with which to make a graph. You have graphing calculators. We've already covered how to graph rational functions. Because of the nature of the year, it's more likely than not that we're actually going to give you the graph and ask you to analyze it. So when the graph is in front of you, it's very easy to do. The function here in question is 3 over x minus 2. So just as a reminder as to where the graph comes from, the vertical asymptote you would get by setting the denominator equal to 0, and that's why the vertical asymptote is here at 2. The horizontal asymptote, you would compare the degrees, and because it's bigger on the bottom, you have a horizontal asymptote here at y equals 0. To find the x-intercept, you would set the top equal to 0, so there'd be none. To find the y-intercept, you'd put a 0 in for the x, which would give you an answer of negative 1.5. So just to give you an idea where the graph comes from. Once you have the graph in front of you, wherever the vertical asymptote is, which in this case is 2, you might be asked to find a limit there. So the first limit you might be asked to find is what happens as x approaches 2 from the negative side. And the second thing you might be asked is what happens as you approach x from the positive side. So you're finding these limits the same way you found any limits graphically. As you approach 2 from the negative side, you're traveling along this branch. As you get closer and closer to 2 from the left side, your graph goes down, down, down. Where is it going to wind up? Negative infinity. As you approach 2 from the positive side, you're on this branch here. As you get closer and closer and closer to 2, it's going up, up, up. We're going to call that infinity. Now, a couple of days ago, when we were talking about limits that went to infinity, we called those do not exist. We are now allowed to use infinity and negative infinity as long as it's appropriate. Same function here, but just showing you what it would mean to go to infinity from a table. So it's the same equation. You're approaching 2 from the left and from the right. You can see that on the left-handed approach, the numbers are getting smaller and smaller and smaller. That's your negative infinity. From the right-handed approach, they're getting larger and larger and larger as they get closer to 2. So that would be your positive infinity. And then this is just a summary of what it is we found. The limit as you approach 2 from the left is negative infinity, and the limit as you approach 2 from the right is positive infinity. So if you thought that was easy, good, it is, but let's try a couple others just to be sure. So here's an example right here of 1 over x minus 1 squared, and it wants you to find the limit as you approach 1 from the left and from the right. So let's go ahead and start by finding the limit as x goes to 1 from the right side of f of x. If we're approaching as x goes to 1 from the right side, we're on this branch right here. As we get closer and closer and closer to 1, you can see the graph is going all the way up to positive infinity. Let's say that we were doing a left-handed approach. So approaching 1 from the negative side, that means that we would be on this branch right here. And again, as you get closer and closer to 1, you can see that the graph continues to go all the way up to positive infinity. Again, make sure you remember the reason why the vertical asymptote is here at 1 is because that's what makes the denominator 0. Then a third question that I could ask you is, now that I've asked you for the left-hand approach, and now that I've asked you for the right-hand approach, what if I asked you for the full limit at x equals 1? Well, just like all the other left-hand and right-handed limits, you would have to compare them. If the limit from the left is the same as the limit from the right, you can say that the limit does in fact exist, and that would be the answer. So it's positive infinity for everybody from the left, from the right, and for the final answer. Similarly here, let's have negative 1 over x minus 1. Again, the x minus 1 in the denominator, again, tells us that the vertical asymptote is going to be here at 1. Let's first consider what's happening as we're approaching 1 from the positive side. Then we're going to consider what happens as we approach 1 from the negative side. And then we're ultimately going to consider what happens if we just approach the full limit. The magic number, in this case 1, has to be wherever there's a vertical asymptote. If there were multiple vertical asymptotes, I could ask you to find the limit at one of them or both of them, but it has to be a vertical asymptote in order for infinity to be possible. So as I approach 1 from the positive side, I'm going to be on this branch here. Because I'm going all the way down, we're going to call that negative infinity. As I approach 1 from the left-hand side, the graph is going all the way up. We're going to call that positive infinity. And then finally, for the full limit, because one of them goes to positive and one of them goes to negative, that means that the limit for the full limit, does not exist. And that should make sense. Remember, for a limit to be possible, both sides has to be going to the same place, which clearly they are not. So a little reminder about rational functions, since again, it has to be a rational function in order for a vertical asymptote to be there. Recall that vertical asymptotes are things that make the denominator equal to 0 for uncommon factors only. Remember that a vertical asymptote is a non-removable discontinuity, and there can be any number of vertical asymptotes greater than or equal to 0. So you could have none, or you could have 1, 2, 3, 4, 20 of them. Remember that a whole is the result of a common factor, so that's why factoring the problem is very important, and these are called removable discontinuities. And there can be any number of wholes greater than or equal to 0. It's possible there could be none, or there could be as many as we feel like giving you. When it comes to finding infinite limits for rational functions, which is really kind of the whole point of this lesson and the whole point of the homework, you have a couple of different options for how you do that. The first of which is you can sketch a graph of the function, either by hand or by using a graphing calculator. Just a warning about the graphing calculator, the asymptotes obviously don't show up. They're not graphed. It's kind of implied that they're there, but you might either have to zoom in or zoom out. And either way, you still have to know the basic rules of rational functions in order to interpret what you're seeing. That's why sometimes it is easier to actually just sketch it on your own, but we leave that up to you. As a reminder, let's say you have the rational function x over x squared minus 9. Here's what the picture would look like. Again, if you want, plug this in your graphing calculator and see if it looks the same. You know that the asymptotes should be there. So if they're not showing up as plainly as you would like, again, you kind of have to know that they're there in order for the graphing calculator to be a useful tool. So just to point out some of the important points here. So the x and y intercept in both cases is 0. You would get that by either setting the numerator equal to 0 or by putting a 0 in for all the x's. The horizontal asymptote would be here at y equals 0, because if you compare the degree of the denominator is greater than the degree of the numerator, which of course means that there is a horizontal asymptote at 0. Remember, if the degree was bigger on the top, there would be no horizontal asymptote. And if they were the same degree, then you would do the coefficients. How do you know where the asymptotes are? Well, you factor the bottom, x plus 3, x minus 3. Because of the fact that there were no common factors, that's how you know that they are vertical asymptotes as opposed to being holes. And then once you have all that information, you could then continue to plot additional points as needed. And that's how you would get the graph that is shown. Remember that even though at 0, 0, you are crossing the horizontal asymptote, that's okay. Horizontal asymptotes by definition are considered end behavior. So you would have to approach the horizontal asymptote all the way to the left side of the graph and all the way to the right side of the graph, but you are allowed to cross it in the middle. So don't forget that that's an option. Once you have the graph in front of you, again, whether you did so via graphing calculator or whether you did so by hand, an example of a question that I might be able to ask you is I might ask you for the limit as x goes to 3 from the positive side. Again, it has to be at an asymptote. So we're talking about positive 3. It could just as easily have been negative 3, but if you understand one, you probably understand both. So as you approach 3 from the positive side, that means that you're on this branch right here, which means that you're getting higher and higher and higher, which means that you're going to infinity. Then let's say that you were approaching the limit as x goes to 3, but from the negative side. That would mean that you're on this branch, which means you're getting smaller and smaller and smaller, which means you're going to negative infinity. And then finally, let's say we just want to know what about the full limit as you approach 3? Well, if you compare the left side approach and the right side approach, sadly, they are not the same. So you would have to say that that limit did not exist. So that's your first option for finding infinite limits for rational functions, which is really the majority of what tonight's homework is. You can either create a graph by hand or using the graphing calculator. It doesn't matter which one you do, as long as you're able to interpret it. And then the second way, so notice this is the same equation, is you can do so algebraically. In order to do so algebraically, you have to plug nearby x values into the equation from the appropriate side. So what does that actually mean? Well, let's say that you were trying to find the limit as x goes to 3 from the right side of this function. You would essentially pick a number that was close to 3, approaching it from the right-hand side. So let's say maybe 3.5. If you were to choose a value of 3.5, you would literally plug it in. So 3.5, 3.5 squared minus 9. If you were to calculate the top number, you would get 3.5. If you were to calculate the bottom number, you would get 3.25. And here's where you have to be able to understand what you're getting. The truth of the matter is 3.5 is actually pretty close to 3. So if you divide 3.5 by 3.25, you're going to get a value that's right here on the graph. In order to get a bigger number, you would have to pick something even closer to 3. So 3.4, 3.2, 3.1, 3.0001. But of course, that makes the algebra messier. The truth is, as long as whatever you get here is positive, you can declare that that is going to positive infinity, because the graph would just keep going up, up, up the closer that you get. So again, it doesn't actually matter what that turns out to be as long as it's positive infinity. Consider the opposite as you approach x from the left-hand side. So again, if you wanted to do this algebraically, you would choose a value of x close to 3, but from a left-hand approach, let's say 2.5. That would give you 2.5 over 2.5 squared minus 9. That would be 2.5 over negative 2.75. And if you were to do that, again, in reality, 2.5 is really not really that close to 3. So if you plug that value in, you'd be getting this point on the graph here. The closer you get to 3, 2.7, 2.9, 2.99999, you're going to get a smaller and smaller and smaller number. But as long as whatever's here is a positive divided by a negative, you can conclude that that is negative infinity. So some people like this approach. Some people don't really understand why that works. You're not going to be told one way or the other of how you have to find the limit, so it's up to you. But this is just another approach if you don't want to have to go ahead and actually graph it. If you do want to graph it though, just a quick reminder of all the different things. Remember to find the x-intercepts, you would set the top equal to 0. To find the y-intercept, you would set the x's equal to 0. To find the horizontal asymptote, you would compare the degrees. To find the holes and the vertical asymptotes, you would have to first factor everything in sight. So on the top, factors of -8 that add up to be +2. That's going to be a +4 and a -2. Difference of squares on the bottom, x plus 2, x minus 2. The common factor, remember, that's the whole. The whole has to be an ordered pair, 2 comma something. It's 2 because it's whatever would have made this canceled factor 0. Then you're going to plug the 2 into your reduced form. So if you plug the 2 into the reduced form, you get 6/4, which means that your whole is the 0.23 And just make sure you remember that a whole is, of course, a removable discontinuity. Then look at your reduced form, which here is x plus 4 over x plus 2. The vertical asymptote comes from setting whatever is left in the denominator equal to 0, which means you would have a vertical asymptote at -2. And important to remember that this is a non-removable discontinuity. Oh, so sorry there, you can ignore that background. Here's Calc homework number 7. So this is section 1.5. It's pages 88 to 89, and then all of those problems right there. As I note there in the specialty at the bottom, that if the problem does not specify how to find the limit, and I'm pretty sure that none of them do, you can either do so with a graph or algebraically. And again, if you're going to do so with a graph, it's fine if you use the graphing calculator. Even if you do, I would draw what you're seeing so that later on when you go back, you know what it says. Or you can sketch it by hand. The ones on the homework are quite simple. But either way, these are the problems. It's possible that that will be the end of your lesson for the day, but depending on how much time is left, we're now going to do a couple of review problems about finding the limit using the difference quotient. These were really back on homework number 3, I believe. And I just think that there were some people who had some questions, so it doesn't hurt to do a couple of extra ones. So for the function 1 over x minus 1, find the limit as h goes to 0 of the difference quotient. So in order to do that, you're going to go ahead and start by finding f of x plus h, which means everywhere there's an x, you're going to put an x plus h. And I'm going to go ahead and put that in parentheses. Minus the original function, 1 over x minus 1. And this is all still over h over 1. So when you're using the difference quotient, you first just start by plugging x plus h everywhere there's an x, and then subtract the original function. Now we're going to go ahead and simplify. So I'm going to leave this as a complex fraction, h over 1 on the bottom. In order to combine the numerator, I'm going to find a common denominator. And the common denominator of x plus h minus 1 times x minus 1 is just those two things being multiplied times each other. That means you have to multiply this value times x minus 1. You have to multiply this value by x plus h minus 1. And because of the fact that this is a subtraction, you of course want to make sure that you are using parentheses so that you can distribute that minus. In the next slide, let's go ahead and actually do that. So that's going to give me x minus 1 minus x minus h plus 1 all over that common denominator. And again, this is all still over h over 1. Then you're going to go ahead and do some cancellation. So the x's cancel, the 1's cancel, and you're just left with a negative h over that common denominator. If you want to get rid of this complex fraction, remember you're going to multiply by the reciprocal, 1 over h. That's going to cancel the h's. And that's going to give you negative 1 over x plus h minus 1 over x minus 1. Now, this original problem was to find the limit. I dropped my limit statement along the way just because it's easier, but you have to make sure that you put it back in the final step. So in the final step, you're going to go ahead and turn the h into a 0. So your final answer is going to be a -1 on the top. It's going to be an x minus 1 times an x minus 1 on the bottom, which we're going to write nice and simply as x minus 1 squared. So your final answer here is -1 over x minus 1 squared. Extra slide in case I needed it. And then the last one here is another one, but instead of using h's, we're going to use delta x's. So a delta x means a change, and that's what an h does as well. So you could see either iteration of it, and we are going to use both, especially in chapter 2. But for some reason, people tend to not like the delta x's as much. But I just want to go ahead and make sure that you can do either of them. So again, to start in the function, everywhere there's an x, you're going to put an x plus a delta x. So that's going to be 8 times the quantity, x plus delta x, the whole thing squared, minus x times x plus delta x. That's what happens if you just plug in x plus delta x. Then you're going to subtract the original function. Don't forget to use parentheses over 8x. And that's all over delta x. So in my next step, I'm just going to do the numerator. So if I just do the numerator, I'm going to get an 8. And then I have to actually FOIL x plus delta x. So that's x plus delta x times x plus delta x. X times x is x squared. X times delta x is x delta x, and there would be 2 of them. So that's 2x delta x. And then delta x times delta x is the quantity delta x squared. So that's just what I get when I do the FOIL. Then I'm going to distribute the 8, so -8x minus 8 delta x. Distribute the subtraction, -8 squared plus 8x. So again, this is just the numerator. I'll put the denominator back in a minute. So now that I've done out all that algebra, I have to go ahead and distribute this 8 to each of those 3 terms. So if I do that, I'm going to wind up with 8x squared plus 16x delta x plus 8 times the quantity delta x squared minus 8x minus 8 delta x minus 8x squared and plus 8x. So then, So from here, again, there still is the denominator, which I'm going to put back in a second. But from here, lots of good things should happen. Good things have to happen in order for you to know that you're doing this right. So the first good thing is that the 8x squareds cancel, then the 8x's. And you should basically only be left with things that have a delta x. So 16x delta x plus 8 delta x squared minus 8 delta x. And this is all still over the original delta x. Remember, I just got rid of it for all those steps so that I didn't get confused. Lucky for me now, I can cancel a delta x from each of the quantities in the numerator, which means I get rid of this delta x, I get rid of this delta x, and I reduce this delta x to a power of 1. So that's going to give me 16x plus 8 delta x minus 8. Then last but not least, remember the whole point of this problem is you were trying to find the limit as delta x goes to 0. So that means you're actually going to take the delta x and turn it into a 0, which means this entire middle term is gone, which means you're just going to be left with a 16x minus